Okay, so we're going to start our discussions on the discrete time equivalent of unit impulse and unit step, and these concepts are pretty much, I mean, very similar to their counterparts in the continuous time. So I'm going to skip over them or go over them relatively quickly. Right. So the first thing I want to talk about is unit impulse signal. So unit impulse and the definition I've actually written down here. So, right. So the definition, according to that definition, the unit impulse is a signal, and which is represented by delta, the notation delta, which is equal to 1 only when n equals 0 and is equal 0 otherwise. Right. So if I were to sketch this out, this signal would look something like this. Right. So it would be equal to 1 at n equals 0, and all other values of n. I mean, this is 1, 2, 3, and so on and so forth. It will be 0. Right. So that's what a unit impulse is. And a unit impulse in the discrete time is relatively easier to understand. I mean, there's no limits involved. There's no area going to 1 and so on. So just equal to 1 at n equals 0, and all of the places on the time axis, it is equal to 0, right? Then similarly, we have something called the unit step function or unit step signal. And the definition of a unit step signal is that the unit step is once again denoted by u of n, which is equal to 1 for all values of n which are greater than or equal to 0 and is equal to 0 otherwise. Right. So unit step is actually a step, right, which goes to 1 at n equals 0 and stays 1 for all positive values of n, non-negative values of n, and is equal to 0 for negative values of n. Right. So if I were to sketch this out, so if this is n, right, so this step resides at 0, and then here, and so on and so forth. And for all negative values of n, this is 0. All right. Now, here's the question. The question is, can we determine a relationship between these two signals? I mean, can I write the unit impulse as a function of unit steps somehow, right? So if you recall, in the continuous time domain, the unit step signal and the unit impulse signal was related how? The unit impulse, we said, was equal to the derivative of the unit step, right? So unit impulse was a derivative of the unit step. What kind of a relationship do you think would hold here? I mean, what would delta of n be as a function of u of n, or perhaps a shifted version of u of n? I mean, so anybody can take a guess कि मैं ये unit step से unit impulse पे किस तरह जाऊं? Can I do some transformations to obtain the unit impulse from the unit step? Anyone? All right, so it turns out that if this is u of n, right? If I take another signal, and let's say, so this is n, and so if I take another signal, which is a shifted unit step, this is 0, this is -1, this is -2, this is 1, 2, 3, 4, 5, and so on and so forth. So what is this second signal as a function? So this first signal is u of n, right? So this is u of n. What about the signal down below? So this is u of n. निचला वाला signal क्या है? निचला वाला सिग्नल क्या है जी? As a function of QZ, what do you think? So what is this signal down below a function? I mean, U of n से किस तरह related है ये? Zan, can you hear me?
Yes, sir, I can.
So what do you think the function down below is as a function of U of n?
Hello.
Ji,
Hello, sir. Sir, am I audible?
Ji, you're audible, yes.
Hello. सर आपकी आवाज सर आपको आवाज आ रही है?
जी आ रही है जी, बिल्कुल आ रही है.
अरे क्या नेट को आवाज दोबारा ज्वाइन करता हूँ.
Can other people hear me?
आप वाईफाई राउटर दोबारा चलाइएगा.
Right. So as people point out, जी Daniel.
सर मतलब मैं कहना चाहता था कि दोनों की आवाज़ें आ रही हैं मुझे और मैं आंसर
Okay, answer. Yes, U of n minus 1. Good, right? So this is U of n minus 1. It's just a shifted to the right, and as people point out in the chat box as well. Now, can I do something with U of n and U of n minus 1 to get delta of n? Subtract the two. Excellent. Subtract what from what, Umar? Umar, unmute करके बता दें. Good, right? So you subtract U of n minus 1 from U of n, right? So, and that would give you delta, and that's clearly visible from the graphs that I actually drew, right? So delta of n is actually equal to U of n minus U of n minus 1, because if I subtract the two, everything cancels out, and the signal becomes 0 at all of the places except that n equals 0 thing that's going to be left out, right? So that should be clear, right? What about the other way around? And that might be slightly more challenging in a sense. Can I represent U of n as a summation of shifted impulses somehow? I mean, this thing that you see here, can I not write this as a summation of deltas, a sum of deltas? Exactly. So how would that pan out, right? So as U of n, if I just look at this figure here, right? So this first thing here is delta of n, right? This second impulse, which is residing at n equals 1, is delta of n minus 1, right? And then there's a delta of n minus 2, and then there's a delta of n minus 3, and so on and so forth, right? So this is actually delta of n plus delta of n minus 1 plus delta of n minus 2, and so on and so forth, all the way up to delta of n minus infinity, actually. So it's all the way up to infinity. Okay. Can I write this as a sum, as a nice notation? Yes, we can do that, right? So this is summation. So this is summation k going from 0 to infinity delta n minus k, right? And that's the relationship between U of n and deltas, right? I can manipulate this a little bit more, right? So if I make a change of variables now, right? So if I make a change of variables and say, okay, let m equals n minus k, then what happens? This summation reduces to, the summation is of m, and when n equals 0, m becomes equal to n. So this is, I'm skipping some steps here. So this is m equals minus infinity all the way up to n. Right? I just make a change of variables and see what happens to m when n equals 0, and what happens to m when n equals infinity. Right? So is there a, okay, so I've been, okay. Right, so there might be internet issues with some people, or there might be something going down here. I'm not sure. Some people say they can hear me well. Some people say there's lacking. But let's try to do what we have. I mean, record our session, so hopefully we can make it up. Okay, Zen? All right. So
Excuse me sir, ये जब k is equal to 0 है तो m is equal to n होगा, तो ये n should go from, यानी कि उसको हम ये नहीं लिख सकते कि n from n go, यानी कि जो summation है
Yeah.
that can go from like जब k 0 to k infinity है तो from, अच्छा वो आपने step skip कर दिया. Okay, सही है.
Yeah, step skip कर दिया, right? So I just made the change of variable, right? So and you can actually see कि यार ये हो क्या रहा है, right? So if I just look at what the summation is, this is delta of n, this is plus delta of n minus 1 plus delta of n minus 2 and so on and so forth, right? So अगर मैं ऊपर से नीचे आना शुरू करूं, this is exactly this is exactly what the expression here was, right? Right, so I'm in that summation, I'm starting backwards from n, right? So when I plug in m equals n, I have delta n. If I plug in m equals n minus 1, I have delta n minus 1, and then delta n minus 2, and then delta n minus 3, all the way up to infinity, minus infinity, right? And delta n minus infinity, right? So this is exactly what you have in that expression above. So right, so 1 and 2 are equivalent, right? So these are the two expressions that we typically use to relate the unit step with the unit impulse, right? And there's a lot more that you can say about this this equation number 2, right? So if I look at this equation number 2, u of n, and somebody were to give me exactly this expression and say, Kiji, forget about ke kahan se aaya, right? And just analyze it and really seek right hand side, is that really equal to 1 for n is greater than equal to 0 or not, right? And if I just look at this right hand expression, right? So if I just look at, let's take a look at m equals minus infinity to n delta of m. So what's really going on, right? What is really going on? So what this is actually an accumulation, if you will, right? So this is an accumulator. And if I were to plot things out or visualize them graphically, right? So if this is m, and delta of m would be just this impulse residing at m equals 0, and all other places, this will be 0. Right? And what does the summation do? Summation is an accumulator which sums the entire signal starting from minus infinity all the way up to n, right? So what if n was here, right? Which is, in this case, is minus 3, right? What do you think the summation is going to be? I'm picking up the entire values of the signal starting from minus infinity and end at n. What do you think the summation is going to turn out to be? All the values in that summation are equal to 0, right? So their summation is going to be equal to 0, right? And regardless of where n is, as long as n is in the n is negative, okay? Daniel, what do you mean for unit impulse?
सर अभी पूछ रहे थे ना कि इस n तक अगर हम n minus 3 पे लें तो क्या वैल्यू होगी, तो मुझे सिग्नल कौन सा है हमारा,
if n equals minus 3 पे रखता हूँ और फिर मैं ये summation ले लेता हूँ, right? So if I compute this summation, I'm summing all zeros, and therefore this sum is going to turn out to be equal to 0, right? So this summation really turns out to be what I found out is going to be equal to 0 for all values of n which are less than 0, right? But what happens if n is positive, right? Let's say this n was here. So n was, let's say, is equal to 0, 1, 2, and this is 3, right? So what happens in this summation, right? Once again, I start from minus infinity. Signal को मैं sum किए जा रहा हूँ, accumulate किए जा रहा हूँ, right? और 0 वाली चीज रह जाती है, right? That's the only non-zero value inside the summation. All other values inside the summation are 0, right? Therefore, the sum is going to turn out to be equal to what? This sum is going to turn out to be equal to 1 for all values of n which are greater than equal to 0, which is indeed the unit step, right? So I've gone about and verified this from another interpretation, another way to think about it, right? So I started from somewhere else, did a change of variables, found out a relationship, and then tried to make sense of that relationship in another sense, another way, Okay, and everything clicks together. I mean, regardless of how I interpret things, right? Everything is going to click together, right? And that's essential, like I always say, for your understanding, take it for your learning, right? So, and I also want to draw parallels to the discrete time or to the continuous time, right? So this is a difference, right? So we're saying that the unit step is, or the unit impulse is equal to the difference between the first difference of the unit step, right? Just like in continuous time, the unit impulse was equal to the first derivative of the unit step, right? So the equivalent to the first derivative in discrete time is actually the first difference, something called the first difference, okay, which is u of n minus u of n minus 1, right? Now, what about the relationship between u of n and delta of n? And if you go back to continuous time, we said u of t is equal to the accumulation, which is integral from minus infinity to t of delta of tau, right? So it's an accumulation of delta of tau, right? And here it's an accumulation as well, except that instead of that integral, I now have a summation, right? So this is an accumulation. Right? So, I mean, there are strong parallels to what we've done in continuous time, right? So this equation number 1 is the first difference. If I take the first difference of unit step, I get the unit impulse. And if I accumulate the unit impulse, I get the unit step, right? And those are inverse relationships, right? Just like derivative and integral are inverse relationships, the first difference and accumulation are inverse relationships, right? Any questions here before I move ahead? Okay, I just want to quickly talk about the sampling properties of unit impulse. So if I give you x of n, and if I multiply with delta of n, what am I going to get? What is this going to be equal to? Anyone? And this draws parallels once again from continuous time discussions.
Sir, x of 0?
All right. Almost there, Daniel. X of 0 के साथ कुछ और भी होना चाहिए, right? So what I'm saying is, okay, let's say x of n was some signal, arbitrary signal, right? So let's say ये कुछ आ रहा था. This was 0, this is 1, this is 2, this is 3, sorry, minus 1, minus 2. And this is the value that was there at x of 0. If I multiply this with the delta function, and that delta function is equal to 1 only when n equals 0. If I multiply these two signals together, what do you get? So you get x of 0, excellent, Hamza, Rashid, it says KG, and other people have pointed out as well. This is going to be equal to x of 0 only at n equals 0, right? And is going to be equal to 0 at all other places. And as a result, I can say that this is actually equal to, so this is going to turn out to be equal to, at n equals 0, it's going to be something which has a height x of 0, and all other places will be 0. What is this equal to? This is nothing but, as Omar points out, this is x of 0 times delta of n, right? Just like what we had in the continuous time. So this is x of 0 times delta of n, right? Now, similarly, if you get what this is, I can, let me ask you this. What is x of n times delta of n minus n naught? Right, just a simple extension of what we've done up above. So what is this equal to? What is x of n times delta of n minus n naught? Right, so Talha says x of n naught, but Talha, uske, Ji Manur, go ahead.
So I was going to say the same thing, लेकिन उसके आगे at s of n,
At
x of n naught
yeah.
into s of n.
नहीं, S कहाँ से आ गया? This is delta, right?
Yes, I thought that.
And delta n minus n naught,
Makes sense.
right?
So,
Excellent, Hamza, right? So because it's going to be an impulse only residing at n equals n naught, and the height of that impulse is going to be scaled by what x was at n equals n naught, right? So as far as this x of n naught is concerned, this is actually just a scaling. This is a constant. Okay? Acha. Let me ask you something else now, right? So what about this summation, right? So where I sum from minus infinity to plus infinity, x of n delta n minus n naught. What do you think this will turn out to be equal to? Right. So if I just use the expression above, or what we, so this is summation n equals minus infinity to plus infinity. This is x of n naught delta n minus n naught. And x of n naught can come out of the summation because it's not a function of n minus infinity plus infinity, and this is delta n minus n naught. What is this summation equal to now? What is this summation equal to? If I sum a delta function, train of Talha, from minus infinity to plus infinity, train of impulses nahi hai ye. Right? If this summation was over n naught, then this would have been a train of impulses, a function of n, right? But what you have inside here, I know this is equal to 1 only when n equals n naught, n is 0 otherwise, right? So as I sum over n from minus infinity to plus infinity, I'm summing infinitely many terms here, but all of those terms are 0 except the term corresponding to n equals n naught, right? And therefore this must be equal to 1, right? So when you say Hamza, wouldn't it be the same? What do you mean by that?
तो जिस तरह पिछला वाला हमने किया x of n delta n minus n naught, वही वाला सर हो गया ना, क्योंकि n naught थोड़ी हम चेंज कर रहे हैं.
बिल्कुल, लेकिन मैंने exactly वो किया, लेकिन I've also put in a summation here, right? So I'm now summing over n as well. So if
बाकी वैल्यूज 0 होंगी तो फिर सम करने से कोई फर्क तो नहीं पड़ना चाहिए.
नहीं, लेकिन अब ये सिग्नल तो नहीं रहा ना. अब now it's going to be a constant. It's not a signal anymore. It's not a function of n anymore. Right? So as opposed to ये देखें, ये equation मैं आपको देता हूँ. This is a signal and this is a function of n, right? What that means is that this signal is equal to 0 for all values of n and is equal to x of n naught at n equals n naught, right? So if I sketch this out, let's say ये n था और ये कोई n naught value थी, और n naught value पे ये signal जो है कुछ x of n naught डिजाइन करता है, और बाकी हर जगह पे 0 है. Now this is a signal, right? Now, and this is equation number 2, if you will. चलो वो 2 मैंने इस्तेमाल किया था. This is 3, if you will, right? Now, what about this equation? What does equation 4 do? Equation number 4 just basically takes this signal in equation number 3, or in this figure here, right? And sums over all values of n, right? ये भी इस ये लो सबको sum करते रहो. Everything sums up, right? But when everything sums up, everything is 0 except this term here. And this is x of n naught. So when you do that summation, I mean, this is going to turn out to be equal to x of n naught, right? Just like what we had in the continuous time, by the way, right? So is strong parallels to module 1. Okay, except that instead of the integral now, we have a summation now, which is a discrete summation. Okay. Any questions? I'm going to continue this discussion in the next module. I mean, the related discussions. All right. So, I mean, building on top of this, what we want to do next is talk about discrete time LTI systems, right? And in particular, the convolution sum, right? So just like we had convolution integral in continuous time, we have convolution sum in discrete time, right? Now let me begin with this this sifting property in which is actually related to the discussion that we just had. Right, so let's start with an example, right? So if I give you a signal, right, which is x of n, and let's say this was equal to so -1 पे ये है, 0 पे ये है, 1 पे ये है, ये है, और yeah. So this is 1, 2, 3. The height here is 1. The height here is 0.5. The height here is 0.5, and the height here is 0.5 as well, right? So this is x of n. Now, can I write this x of n as a train of impulses? Can somebody help me here? And all places else this is 0. Can x of n be written as a train of impulses or some summation of impulses?
Sir,
Ji, Daniel.
sir, 1/2 x, 1/2 delta of n plus 1.
N plus 1, excellent.
Plus delta of n.
Right.
Plus 1/2 delta of n minus 1.
And let me just say that this is 0 times delta of n minus 2 and plus 0.5 times delta n minus 3, right? And so on and so forth, right? And because everything else is 0, right? If I can quickly generalize this a little bit and say, this is actually equal to x of minus 1 times delta of n plus 1 plus x of 0 times delta of n, because this was 1, okay, plus whatever the signal was at x of 1 times delta n minus 1 plus whatever the signal was as x of 2 times delta of n minus 2 and whatever the signal was at time n equals 3 times delta of n minus 3, right? And I clearly see that the signal can be represented as a train of impulse. Can I generalize this a little bit? Let's say if this was any signal in general, right? I could have actually said x of n is equal to, and this would be x of, let's say, minus 3 times delta of n plus 3 plus x of minus 2 delta of n plus 2, right, plus x of minus 1 times delta of n plus 1, and so on and so forth, right? So and x of 0 times delta of n plus x of 1 times delta of n minus 1, and so on and so forth. चलो एक और कर सकते हैं, x of 2 delta n minus 2, right, all the way up to infinity, right? And I can write the summation, and I say, okay, this is actually equal to summation k equals minus infinity plus infinity. I just want to represent this mathematically compactly, right? So x of k times delta of n minus k. And this is x of n, right? And this is called the sifting property of, so in which he just says, a discrete time signal can be represented as a superposition of scaled and shifted impulses, right? Just like what we did in continuous time, right? Continuous time, we had an integral, right? And that scaling, we did that shifting, but then the summation was not actually discrete summation, but rather an integration as a continuous summation, right? As opposed to that, in discrete time, we have the same parallels, except that the integral is replaced with the summation, okay? So any signal, any discrete time signal can be represented as a superposition of shifted and scaled impulses, right? That's what the sifting property is, right? And this sifting property is used to characterize LTI systems, just like we did in continuous time as well, right? So let's do that. Okay, so LTI systems, I don't think I want to say a lot more about this. LTI systems, we've discussed linear and time invariance, right? So we're just discussing the counterparts, the discrete counterpart. So any system which is linear and in time invariant, right? We're going to say that's called an LTI system. And the input is discrete and the output is discrete, right? So LTI systems, if you can, somebody can remind me what properties, what did linearity imply and what did time invariance imply, right? So if I have a system in which the input is x of n and the output is y of n, what does linearity mean? Quickly remind somebody, right? So itni baar kiya hai, should be on your fingertips, right? So what does linear, when a system is linear, what does it mean? So nobody remembers what a linear system is? Or people would like to plead? Right, so Ji Manur.
Sir, again, I have trouble putting it into words. Again, it's like when you input may you put like a linear change, so output maybe you get like the same linear change. Like so, if it's like a times
Okay.
a times into input something, so you'll get a that same relationship like input output.
Okay, okay, good. Marine, do you want to say something?
Sir, I wanted to say that it basically means that, like Manur said as well, that the linear change, but I also remember that if two like signals are added and then they're being multiplied by some constant,
Okay.
so their output will be as if like, each of them had individually been put into the system and then summed up. I don't know how to put it in words exactly.
That's excellent, right? So if I sum the inputs in this fashion, so if I have a superposition of the inputs x1 and x2 in this particular fashion, capital A, which is a constant, times x1 plus capital B times x2, the output is going to be the respective superposition of the outputs of the individual outputs. Okay? So mathematically, this is what it means, right? So अगर मुझे x1 का y1 पता है, x2 का y2 पता है, then if I have that superposition in the inputs, the outputs also superpose in the same fashion, right? As Zainadim also says in the chat box. Okay, good. Now, what about time invariance? What time invariance? Give me a minute. Hold on. All right, what about time invariance? So, Ji Manur.
Sir, so time invariance is like अगर हम input में कोई time delay या कुछ भी ऐसा लाएं, so we're gonna get the same time delay in the output too. So that would be like time invariant. फर्क नहीं पड़ रहा उसमें.
Excellent. Right. So if I shift the input by n naught, the output is also going to be shifted by the same amount, and that's time invariance, right? So this is time invariance. So now that we have a quick recall of what LTI systems are, what we want to do next is to try to determine some characteristic of an LTI system which would completely characterize it, right? Or some property of the LTI system which would completely characterize its behavior or the input-output relationship, right? And for continuous time LTI systems, what was that, by the way? Kya cheez hoti thi? That was something called the बोल दे यार कोई. There was something called the What was something in the
सर आप सवाल रिपीट कर
आपने क्या पूछा?
LTI systems की परफॉर्मेंस को completely characterize करने के लिए आपको LTI system के बारे में क्या पता होना चाहिए? क्या चीज एक ऐसी चीज है?
Impulse response.
Impulse
Impulse
response.
response.
Right? Impulse response. Excellent, right? And something similar holds true here as well. Actually, exactly the same thing holds true here as well, right? So let me say, Kajit, if the input of an LTI system is a unit impulse, let the output be denoted by h of n. And this h of n is called the impulse response, right? So impulse response, once again, by definition, is the response or the output that you get when the input to that system is a unit impulse, right? That's the impulse response. Now, because of linearity, if I multiply or because of time invariance, really, what is going to happen if my input is delta of n minus k? So फिर output क्या होगी? The output is going to be h of n minus k, right? And that's because of time invariance, right? If I multiply the input with x of k, remember everything is a signal, and that signal in the independent variable is time n. So k is nothing but a constant. So if I multiply delta of n minus k with x of k is a constant. So if I multiply the input by a constant, the output must also be multiplied by the same constant. And that's because of linearity, right? Now, if I sum the input over all k, the output must also be summed in a similar fashion. Why? Once again, because of linearity, right? But what do I have on the left-hand side? This is nothing but x of n, as we've determined in the sifting property up above, right? And from here, what we've been able to conclude is, or derive, is the fact that if the input to an LTI system is x of n, the output of the LTI system is given as this convoluted looking summation, right? This is x of k times h of n minus k, right? And this convoluted looking summation is called nothing but the convolution sum, right? Just like we had the convolution integral, now we have the convolution sum in the discrete time case, right? So this is called the convolution sum. And you can draw parallels, you can draw intuition, just like what we did in the module 1, right? What does it exactly really mean, right? This is, once again, like we did in the continuous time, is scaling, right? And memory, right? So if there's a memory, past के elements को इतना scale करना है, फिर उसके इतना scale करना है, and you just sum it up, right? So all of that intuition still applies here as well. Okay, so as a conclusion, let me write this out at the bottom, right? So the convolution sum is given as this summation. So the output of an LTI system, when the input is x, is given as this expression. Right? Any questions here? So I can now start doing some examples to try to make sense of what it means. Okay, अच्छा, by the way,
this is जिस तरह वहाँ पे हमारे पास convolution का expression होता था integral वगैरह, so इसमें हम questions को solve करते हुए ये use करेंगे. That's the main idea.
Yeah.
Convolution.
Yes, exactly. But instead of an integral, now you have a summation.
You have a summation.
Right? Now, I can derive an alternate representation for convolution as well, by the way, right? So, if I make a change of variables, and I say kg, right, n minus k equals m, right? Then what can I say about y of n? Then y of n is this summation, And as n goes from minus infinity to plus infinity, k also goes from minus infinity to plus infinity, right? So this k also goes from minus infinity to plus infinity. And this is x, and k is n minus m. All right, so sorry, this is m. This is n minus m, and this is h of m, right? And if I just change m with k, right, doesn't make a difference, right? Because that's the name of a variable, just like we did in the continuous time, right? So k equals minus infinity to plus infinity, and this is h of k and x of n minus k, right? So this is an alternate representation, right? And which is an equal representation, by the way, right? So both of them are exactly the same, right? And I say, okay, y of n in this case is x of n convolved with h of n, which is the same as h of n convolved with x of n, right? So it's commutative, just like we did earlier as well, right? Now, if you want to make some intuitive sense of what this represents, or the convolution represents, I mean, that intuitive sense may be represented from this expression here, from this one here, and which is, okay, let's do one example, right? If I give you an LTI system जिसका impulse response ये है, impulse response ये 1 है और फिर ये half है, and then this is 1 by 4. So this is 1, this is half, and this is 1 by 4. This is 0, this is 1, this is 2, and everywhere else this is 0. So this is h of n, right? So if I just look at equation number 4 and plug this in, so I see that y of n is equal to summation k going from minus infinity to plus infinity h of k times x of n minus k, right? But I see that h of k is non-zero only for 3 values of k, and that's 0, and that's 1, and that's 2, right? So this is h of 0 times x of n plus h of 1 times x of n minus 1 plus h of 2 times x of n minus 2, right? And this should give you an idea and some intuition behind what convolution really does, or what the impulse response really represents. So if I give you an impulse response in a LTI system, which is this equal to 1 and then half and then 1 by 4, what this means is कि this 1 means कि signal की exactly copy output में आएगी, right? This half means कि then there's going to be another copy in the output, and that copy is going to be the input shifted by 1 but scaled by half, right? And then there's another copy which is a copy of the input but shifted by 2 samples and then scaled by 1 by 4. And then at the end, all of these 3 copies add up, right? So it's like that echo chamber that we talked about. Ek direct path hai, and then there's a path that comes in after a certain delay, and then there's another path that comes in after another delay and suffers an attenuation, right? So this impulse response gives you information about what the scalings are with different delays, right? So that's what impulse response does, and convolution does. Okay. Any questions here before I talk about specific examples? Right. Okay, so I think I have a separate section on examples here. Right, so this is example 1, right? I have x of n, right? And I have h of n, which is equal to these 3 impulses residing at 0, 1, 2. Okay? X of n at time n equals 0 is 0.5, at time n equals 1 is 2. And I wish to compute the convolution of these 2 signals, right? So how do I go about this? I just look at what the expression was. The expression was y of n equals summation k equals minus infinity to plus infinity, and I'll take the liberty of using this expression, x of k times h of n minus k. So my tablet is h of n minus k, right? And then I see k x is non-zero only for n equals 0 or k equals 0 and for k equals 1. So this is 0.5 times h of n plus 2 times h of n minus 1. Right, and that's my output. Jeetala.
Are these impulses?
This is a signal, right? Signal जो signal discrete time signal है, right? Discrete time signal is defined for discrete values of n only, right? And this x of n is a signal which is equal to 0 for all values of n except n equals 0 and n equals 1. और n equals 0 पे 0.5 है, n equals 1 पे 2 है. And yes, you could say that
actually हम impulses के ऊपर arrow बनाते थे top पे,
but we don't do that. We don't do that in discrete time. Right, because discrete time में the height is not infinity as opposed to continuous time, right? So that's a key difference.
Yeah.
Right? Acha. So y of n equals 0.5 times h of n plus 2 times h of n minus 1. Right? So what do you think the answer should be? If I were to chale, let's do that. Right? So, and Ajit Allah, do you still have a question? Right. So what should y of n be? Because I know what h of n is. What is 0.5 times h of n plus 2 times h of n minus 1? I mean, you could draw these separately, right? So Daniel, u of n minus u of n minus 2, you're saying that's h of n? Is that what you're saying?
Sir, yes, steps में नहीं इसको हम कर सकते step functions
कर सकते हैं, right? If that's how you want to do it, you're welcome to do that, right? So we are saying that the h of n is equal to u of n minus u of n minus 2. That's what you're saying, right?
Yes, sir.
But I'd say there's a slight bit of a problem here. Okay, u of n क्या होता है? u of n 0 से start होता है, 1 पे होता है, 2 पे होता है, 3 पे होता है, 4 पे होता है. u of n minus 2 कहाँ से start होता है, दानियाल?
Sir, 2 से?
2 से, right? तो अब मैं u of n minus 2, right? So ये भी ले लेता हूँ. Blue में से pink subtract कर देता हूँ. What am I going to get?
0 or 1.
0, 1. But that's not what h of n was, right? I mean, these are the only two impulses I'm going to get when I subtract them.
उसका minus 3 कर देंगे.
Yes. Manur?
Sir, अभी हम y of n draw कर रहे हैं ना?
नहीं, अभी वो दानियाल pointed out कि जी h of n को मैं ये क्यों नहीं use कर लेता?
Okay.
Right? So just going back to, which is a common mistake. So this is n minus 3, right? It's not n minus 2. Right? So if you go by that principle, right? So this implies that y of n is equal to 0.5 u of n minus 0.5 u of n minus 3 and plus 2 times u of n minus 1 minus 2 times u of n minus 4. And that's a perfectly fine solution. Go ahead and do it. That's perfectly fine. Okay? But what I want to do is instead let me just look at h of n and just try to figure out what is 0.5 times h of n plus 2 times h of n minus 1. Okay? So I just want to look at this graphically and compute the following. 0.5 times h of n plus, and let's say this is 2 times h of n minus 1. Right? So So let me skip this. I'm a skipping step here. The answer you're going to get is 0.5 here. Okay. And then this is going to be 2.5. And then this is going to be 2.5. And then this is going to be 2. And then it's 0. So this is 1, 2, 3. Take my word for it. You should be able to do this graphically, right? Right. But what I want to do more importantly is something called the flip and shift interpretation, right? Just like we did in the continuous time, right? Yahan pe flip and shift interpretation, what would that mean? Right? So if I look at the flip and shift interpretation or try to perceive what the flip and shift interpretation is, what I do is I try to visualize this x of k as a function of k and this h of n minus k as a function of k, right? And this x of k is what you see here. If the x-axis is k, x of k is this original signal that you had, right? Which is x of k, right? And then h of n minus k is actually a flipped version of h and then a shifted version of h, right? So if I flip this h around the axis, right? So then I'm going to have impulses at 0 and -1 and -2. And then I'm going to start shifting it by n. So if I shift, if n is positive, the shift is going to be to the right. If n is negative, the shift is going to be to the left, right? So that the rightmost end is at n and then n-1, and that in this n-2, right? So this particular case that you see on your screen here corresponds to the fact that this is the case that n is less than 0, right? And then what would y of n be? Y of n for this particular n would be the multiplication of x of k and h of n minus k. You multiply the two signals together, and then you sum everything up. Okay, you sum everything up. So when n is less than 0, what do you get? So n is less than 0. Then what can I say about y of n? Just by looking at this flip and shift. Is there an overlap? No. So excellent, right? So people say, so Talha, so this is 0. Okay, there's no overlap. Achha. Then I start shifting, right? So I n ko mazid aur aage leke jate hain, right? So let me do some tricks here. So n equals aage leke gaya main, and this corresponds to exactly the case when n equals 1. Right? And I've shifted to the right. And this is why this is called the flip and shift, right? So when you flip and then start shifting. The second case corresponds to n equals 0. What is y of 0 here? Excellent, Allah, right? So this is 0.5 because I multiply these two signals together and then I sum them up, right? But since there's overlap only at one place, right? And that place is n equals 0 or k equals 0. And that multiplication is 0.5, and therefore the summation is 0.5. Right, excellent. Now let's shift this even further. Right, so this corresponds to n equals 1 now. Right, so this is n equals 1. So what is the signal at n equals 1? Right? What is going to turn out to be equal to 2.5? Excellent, right? Why is it 2.5? Because I'm multiplying these two things together. Ye multiply kiya, right? When I multiply these two together, what I get is I get 0 at all other places, except at n equals 0, I get 0.5, and at n equals 1 or k equals 1, I get 2, right? And I sum everything up, that's 2.5. Okay, so this is 2.5. right? Then what? Let's do n equals 2. n equals 2 पे I just take the entire thing, ठीक है, and then shift by 1, ठीक है. So this corresponds to n equals 2, right? So once again the summation is going to turn out to be equal to n equals 2 पे is 2.5, right? And then finally let's do it for n equals 3. What happens at n equals 3? n equals 3 पर you shift it again and you get here, ठीक है. This is n equals 3, right? And y of 3 here is, what is this going to be equal to? Y of 3 क्या होगा, right? So it's 2. Excellent. And Daniel, इसके बाद आप नहीं बोलेंगे. Let's see if I can. And then I shift it again. And this is n equals 4. Right? And clearly n equals 4. This is n equals 4. Manur, excellent Manur, right? So at n equals 4, y of 4 equals 0. And so on and so forth. For all values of n which are greater than now 4, you'll get 0. And you compare this with the result that we got there, exactly the same result. So this is the flip and shift interpretation, right? And I'm going to follow the flip and shift interpretation for other examples, right? So this is example number 2 now, right? So this is alpha raised to power n u of n. That's your input signal where this alpha is between 0 and 1. So it's a positive number, but less than 1, okay? And your impulse response is the unit step. H of n is equal to u of n, right? And you need to determine the output, which is the convolution of x and h, right? Now, I will once again utilize the same flip and shift interpretation, and according to which y of n is equal to this summation x of k times h of n minus k, where this k goes from minus infinity to plus infinity. Okay? So essentially, I'm interpreting x to be a function of k, with k is the independent variable, and then it is h that I flip and start shifting, right? So when I do that flipping and do that shifting, so this particular case that you see on screen corresponds to the case when n is less than 0, right? And moreover, because alpha is between 0 and 1, that's a decaying exponential, right? It exponentially decays, right? All right. So what about this case? For n is less than 0, what would the output be, right? You're multiplying x of k with h of n minus k, and you get a product, the resultant, and then you sum that resultant from minus infinity to plus infinity. So when you multiply these two signals for n is less than 0, what do you get? The answer is 0, because there's no overlap, right? There's no overlap, and clearly for n is less than 0, y of n is going to be equal to 0. Now comes the case when n is either equal to 0 or greater than 0. So let me pull this thing here to an arbitrary sum n, okay? And this is n is which is greater than equal to 0. Okay? Yeah, I mean this particular case for n equals 4. Salah, what do you mean? Will we have a rising exponential at the end?
Actually, the shape would be, it would rise, but with the following gradient. That's what I was trying to say. Okay, and पे हमारे पास shape आएगी. So on 0, हमारे y of n पे we have 1. उसके बाद it will start rising until the gradient falls. So for सारा वो अगर हम if सारे points को join करेंगे y of n.
Yeah, लेकिन जो है, so but it would saturate, it would not rise, keep on rising.
हाँ, वही मैं कह रहा हूँ ना, gradient fall करता जाएगा तो at a point जहाँ पर वो
excellent, Excellent. Like let's try to do this, right? So you're
yeah.
Oh, what happened? So you're basing this on some of your intuition, right? Like let's
basically वही मैंने I did it in my head एक किस्म का, yeah, ठीक है.
जी, फिर से कहिएगा.
Yes. See, I did it the convolution in my head.
Okay.
But,
Okay. Good.
so yes.
Excellent.
Yes.
So Manur is on a roll, right? So Manur says this is e raised to power n h of n sum from 0 to n, something close, yes. So the first thing is that the overlap is from where to where. Ji Manur, let's do the honors, right? So the overlap is where to where?
Sir, from 0 to n.
Right. So this summation is going to go from 0 to n. And what am I summing? Right. What I'm summing is alpha raised to power k. And what is h of n minus k within this interval? Manur?
Yes, sir. I was thinking.
ये h of n minus.
मुझे यही बात समझ नहीं है कि हम n minus k क्यों कर रहे हैं?
Because that's what we started out with, right? So the derivation जब सारी कर ली थी हमने, right? उसके आखिर में ये यहाँ पे h of n minus k. You see, this is the definition. You should just. This is what we're using, right? And we're just plugging in h of n minus k here. And I see for all values of k between 0 and n, h of n minus k is this thing here, right? And the height for all of the values within this interval is 1. Because it was unit step third, right? So this is just 1. This goes away. I mean, you're multiplying alpha raised by k with 1. Doesn't matter. Okay? And this is essentially what you have to find. What is this equal to?
Sir, it would be e raised to the power of. I'm not sure.
Right. Okay, that's fine. Right. So this is 1 minus alpha in the denominator, and 1 minus alpha raised to power n plus 1 in the numerator. Okay, so this is 1 upon 1 minus alpha times 1 minus alpha raised to power n plus 1. And if you sketch this out, right, you would get something which looks exactly like what Talha suggested, right? So you're going to have something rising, and then it's going to start saturating, right? And it's going to saturate to what value? Saturate to 1 minus alpha, 1 upon 1 minus alpha. And that's where this is going to saturate to. Okay? And if I were to combine this equation number 1 and equation number 2 nicely in a compact fashion, what can I say? So एक equation से मैं represent कर सकता हूँ दोनों cases को. Can I represent both of those cases with just a single expression? जी Talha.
Add a u of n.
Add a u of n. Right. So 1 upon 1 minus alpha times 1 minus alpha raised to power n plus 1 times u of n. और Talha इसको plot करके देखेगा for alpha any between 0 and 1, you'll exactly get what you suggested. Okay. All right. Let me do another example. So example number 3. Right. So I have x of n is equal to 2 raised to power n u of minus n, and h of n equals u of n. Okay. And I wish to compute the convolution. The convolution, of course, is y of n, which is equal to summation k going from minus infinity to plus infinity, x of k times h of n minus k. right? Right. So what does x of k look like? If I were to plot this out, x of k as a function of k. So it would be minus infinity to 0. Excellent, right? So it exists on the negative side because there's a u of minus n. What this, I mean, signal kisan dikhega? I mean, exponentially, yeah, exponentially rising up to 1. Excellent, right? So this would be 1 here, okay, and then half here, and then 1/4 here, and then 1/8 here, and so on and so forth. Right, so this is 0, this is -1, this is 2, -2, this is -3, and so on and so forth. And all of these are values are zeros, right? So this is x of k, which is 2 raised to power k u of minus k, right? What about h of n minus k? So h of n minus k, once again, going to be two cases. The first case, let's consider this case to be right. So this is h of n minus k, and this h of n minus k. So this is n here, and this particular case that you see on your screen corresponds to the case when n is less than 0. Okay, so that's my case 1. Right, so n is less than 0. Okay, so what would this summation be? So y of n, let me write this again. So this is summation k going from minus infinity to plus infinity, x of k, h of n minus k. So what does this multiplication do to the limits? Right, overlap kahan se kahan tak karna, right? So the summation is from minus infinity to 0. Daniel, is that what you're saying? Right, so this n, remember, n is here, right? So the overlap is going to be, so for example, n equals -2, right? If n equals -2, यहाँ पे और यहाँ पे तो overlap नहीं है, right?
सर मैंने उसको अपडेट कर दिया.
Okay, Manor, excellent, right? So Daniel says as well. So the summation is going to be from minus infinity to n, right? And what do I have inside x of k here? X of k is 2 raised to power k. And what is h of n minus k within this interval? H of n minus k within this interval is 1, right? So essentially, this is what I need to evaluate. How do I evaluate the summation? For that, I make a chain of variables and say, okay, let m equals minus k, right? Then y of n is equal to summation m equals, or so this is going to be slightly different, right? So this is, मैंने कर लिया तो इसी तरह चाहते हैं. This is not what was required. Okay, 2 raised to power minus m, right? And m goes from where to where? M goes from minus n all the way up to infinity. Okay, but this is something that I'm not too familiar with, right? So मैं क्या इसको कर सकता हूँ change करने के लिए, so that I get what I want. क्या ख्याल है?
लिमिट्स चेंज करेंगे, माइनस इंफिनिटी को ऊपर ले जाएंगे, माइनस इंफिनिटी नीचे आ जाएगा.
Again, the kind of summations that I'm familiar with, right? The kind of summation, so this is 2 raised to power minus m is actually equal to half raised to power m, right? The kind of summations that I'm familiar with involve a summation from m equals 0 to infinity. Minus n से infinity तक भी जाती है वो. So I need to somehow change that limit at the bottom to 0, and that's one way to do it. Daniel, excellent, that you can break it down into pieces, right? Because n is negative, so minus n से infinity तक sum करने का मतलब ये है कि पहले मैं minus n से 0 पे करूंगा और फिर 1 से infinity करूंगा, right? That's one way to do it. You break it down into 2 pieces, right? But there's another nice way I can use, जो कि मुझे शुरू में कर लेना चाहिए था, लेकिन क्योंकि I was committed there, तो जब यहाँ पे मैं कहता हूँ I make another change of variables and I say कि let s equals m plus n, right? What does this change of variable do? What it actually does is if m equals minus n, s goes to 0, right? So that when m equals minus n, s goes to 0, right? And that would make my life a lot easier. I'm just plugging in the formulas or relationships that I'm familiar with, right? So using this substitution, what I get, therefore, is this is y of n, and this is summation, and this s goes from 0 to infinity in this case, right? And this is half raised to power m is s minus n. Okay, and therefore this is equal to 2 raised to power n times s equals 0 to infinity, and this is half raised to power s, right? Now it's quite easy to solve, right? So this becomes equal to 2 raised to power n, and what do I have in the summation? This is equal to nothing but 1 upon 1 minus half, right? ये किसके बराबर हो जाएगा? Right, so this is 0.5, this is 2, this is 2 raised to power n plus 1. Okay, so this particular case, mind you, was a case when n was less than 0. Achha. What about the case when n is greater than or equal to 0? What happens there? So ab jo hai, I can pull this up ahead, right? And this corresponds to the case when n is greater than or equal to 0. अब यहाँ पे summation कहाँ से कहाँ जाएगी? If I multiply the two together, where's the overlap? The overlap is excellent, is from minus infinity to 0, right? And that's where the overlap is, right? So this case number 2 is when n is greater than or equal to 0. And for that case, y of n is equal to this summation k going from minus infinity to 0. And I have, this is 2 raised to power k, right? And I make a change of variables. I'm skipping steps here. This is m equals 0 to infinity, and this is half raised to power m, which is equal to 1 upon 1 minus half, which is equal to 2. Right? So for all values of n which is greater than or equal to 0, this is equal to 2. And for all values of n which is less than 0, this is 2 raised to power n plus 1. Ji Dala.
So sigma खत्म कैसे कर रहे हैं? Like 1 over 1 minus. Like,
I mean, I use the
how do we
geometric
figure
series,
this
right?
out?
I use the geometric series. So we cover this in the background material.
Yeah, I remember geometric series.
So I use that that relationship, that infinite sum relationship.
So should we study SAR relations?
So this is the only, so when we did that background coverage, right? So I gave you 2 or 3 relationships. That's the only relationship you need, and everything else derives from there. Okay, but the summations are, I mean, these fine geometric series is going to be a big part of this module. Okay. All right. Right. So this is where I'm going to stop. And by the way, अच्छा चलें, let's finally इसको अगर हमने sketch करना है, sketch कर लेते हैं, चलें जल्दी से. If I'm sketching y of n, what would it look like? So for all values of n which are greater than or equal to 0, the function or the signal is always 2. ये 2 है. What about values of n which are less than 0? That is 2 raised to power n plus 1, right? So this once again is a growing exponential, but now it grows all the way up to 2, right? So यहाँ पे 1 होगा, फिर half होगा, फिर 1/4 होगा, फिर 1/8 होगा. So this is 2, this is 1, this is half, and this is 1/4, and so on and so forth. Right? And you can represent this nicely the following way. So y of n, you can also say this is 2 raised to power n plus 1 times u of minus n minus 1 plus 2 times u of n. That's another way to say this, right? Any questions?
सर इसका मतलब है कि जो हमारा ओरिजिनल सिग्नल था x of n उसका एरिया 2 था.
ओरिजिनल सिग्नल उसका एरिया 2 था. Yes, it was 2. But Daniel, बस just one small point. In discrete cases में हम एरिया की बात नहीं करते. But I know what you're meaning. I mean, you're saying the accumulated values.
Yes, sir.
और वो 2 ही थी, बाकी थी, क्योंकि असल में ये जो चीज थी accumulated value ही तो है. Is that what you're saying? Is that why you're saying this इसकी accumulated value 2 थी?
नहीं सर, वो जो केस, हाँ सर, यही कि n is greater than 0 पे जो है वो मुझे 2 ही रह रहा है.
हाँ 2 ही रह रहा है ना, because that's the accumulated value. That turns out to be 2. That's true. All right. So I'm going to stop here. Any questions?